Y los demás estudiantes se fueron de... ¿Están oyendo la tesis de Jocelyn o se fueron a la playa? So many people are missing today.
Ya están cansados, profe.
Ah, pues cansado del curso
Por todas las clases.
Ah, sí, ha estado intenso, ¿no? Entonces creo que agradecen
Sí.
en lo que estamos haciendo de darles un par de días libres para que se
Sí,
pongan al día.
muchísimas gracias.
Perfecto, muy bien. Espero que no me caiga encima ahora la Cancillería, pero bueno, vamos a ver. Solo es para apoyarlos a ustedes.
No creo, ojalá que no, profe. Nosotros le defendemos.
Eso, perfecto.
Sí, toda la escuela está con ustedes, bro. Apoyando.
Muy bien. Okay, so let's begin. I hope hopefully a few other students will join in, will listen to the recorded class. So let me. Oh, I didn't open my application here. Let me do that. Second. Okay. Very good. Okay, let me start sharing the screen here. Sketchbook. Okay, so I'm going to make a few sort of comments that will be relevant to the homework number 2. So you are a little guided into what I want you to do there. So first I'm going to talk about a very general criteria. General criteria to discard irrelevant diagrams. Okay, so first I'm going to make some picture arguments, okay, and then I'm going to make I'm going to do a second quantize this interpretation of the diagrams, okay. Okay, so I'm going to draw only the interaction part of the diagram, so that you see. For example, we're going to have the interaction line. We know it has some handles here, okay? Remember that these handles, as far as the matrix elements is concerned, this refers to the R prime. So let me draw here. This refers to the R and R prime side of the matrix element, right? Okay, so for example, if I draw I inject the momenta into the diagram like this, okay, this, we have K coming in here, and then let me draw it as I have it in my notes. So we have L here, L coming out, okay, and then again I have injected like this, and I have K coming in and K coming out. So this I don't care. Okay. So I have a propagator. Okay, a propagator coming in here. Okay, a propagator coming in here. Okay, and I have this directions of the arrow. So remember that this is the direction of time. Okay, and so we have a momentum coming in here, another momentum coming out. Okay, L, one momentum coming in, another momentum coming out. So you see that here we have only this corresponds to K greater than Kf, and this, the arrows being in the positive direction, up and down doesn't mean anything in this picture. Okay, so we have a L greater than Kf. Okay, so for the one particle propagator, propagator, yeah, correct. Okay, for the one particle propagator, is this diagram possible? Whatever the connections are outside, okay? Is this diagram possible? Or is it non-zero? Okay, different from zero. Okay, so you notice that here we have, instead of having one particle, the one particle propagator is a propagation of one particle above the Fermi energy. Whatever interactions are going to happen below with the particles below, the virtual interactions. So here we have clearly two particles in this represented in this diagram here. So this diagram necessarily is equal to zero. It does not contribute to the one particle propagator because we have two particles here, not just one. We have two particles. Okay, so this would amount to this interaction sort of makes an additional fermion to either one of the two. So if we are injecting this one, it makes a fermion with momentum L above the Fermi energy suddenly appear from nothing. Okay, so we have, for example, if we inject K, okay, then L appears from nowhere. Okay, so this has amplitude 0, so this cannot happen. Okay, so automatically when you see a diagram which has these directions of the arrows around the interaction, you know that this gives 0 directly. So this can be a piece of a bigger diagram. Okay, if it contains a piece like this, it would be 0. And we'll draw full diagrams at the end of this exercise so you can identify what's going on. Okay. Something else happens with this diagram. What happens if I have now, okay, and now I have this. And I just switch, okay, L with K. Okay, the same thing applies here, same argument. Okay, because remember, the matrix element is symmetrical with respect to R and R prime. Okay, so if we switch R and R prime, which is what we've done here, the same thing, same argument applies. Okay, so is this clear? Okay, we cannot have in any of the processes we're considering two fermions above the Fermi energy because we're trying to address the one particle propagator. So we introduce one particle in the ground state of the interacting system above the Fermi energy, where there's place to put the particle in the first place. So there's no interaction that will make a fermion appear from nothing, okay? So that's the first argument there. If, on the other hand, we have this kind of a propagator, and now we have the opposite direction here. Okay, and we have, for example, K, L, L. Then is this valid? Is this non-zero? Okay, well, you see that now we have, okay, so we're injecting here, we inject momentum, particle with momentum K, okay? So that's a single fermion. And this arrow here, so the arrow of time is going this direction, okay? So this is now pertaining to a hole, okay? Hole, okay, electron. Okay, so now this is possible because now this is exciting. Now L is below the Fermi energy, K is above the Fermi energy. Okay, so this is a contribution to the single particle propagator. In fact, if we just join this line here, okay, let me do it. I'm getting, I think, a little better with colors here. So if we join this line here, we get a tadpole, okay? So this, in fact, is a tadpole. We know the tadpole is different from zero. Tadpole. This would be a simple, the simplest picture or diagram you can draw with this setup of arrows, okay? Okay, so this is non-zero, non-zero. Okay, what happens if I have this diagram? Now I have, again, now I have two arrows here, and I have two arrows here, two handles, okay? So this handle is injecting, ejecting, and this one is injecting, ejecting. Okay, so the choices I'm going to make, so I have K injecting here, I have L going out here, okay, then I have L coming in here and K going out here. What is this? Is this, okay, is this different from zero? Okay, so you see again that we have a single electron propagator. So I inject it with K and I take out with K, and the other ones are, okay, I eject with K, and then this can be an internal line. So both of these propagators are below, so this is below the Fermi energy. Okay, this is also below the Fermi energy. Okay, and these are above, and this one's above. Okay, so if I join here now, this can become a familiar diagram. If I join these two lines here, this is going to become the oyster. Okay, so again, this is non-zero. Okay, so again, you have a single particle propagator above the Fermi sea entering and leaving the diagram. So this is good, okay? And then the other fermion is a hole that's below the Fermi energy. So this is a perfectly viable diagram, okay? Let's see another example. This is an interesting example. Okay, what if I have this guy? I have diagrams of all kinds of colors here. And now I have this guy. Okay, and I have K going in and out. And I have L. What about this diagram? Okay. One thing, again, this is going to be a part of a diagram. Okay. So what if again, this is the arrow of time here. So if I have something like this, I can draw a time, okay, going like this, okay. This is an equal time. This is, for example, a time t. And I have simultaneously an electron, which is below the Fermi energy, and an electron which is above the Fermi energy. Is this possible? Okay. It's not possible because L is a single momentum. It's either above or below. It cannot be both above and below. Okay. So when this happens, then this is zero again. So this is, if you find that at any point in a diagram, you can draw a vertical line, and that diagram, or that vertical line, it includes a propagator, a hole, and a fermion, a hole and an electron, both above and below the Fermi energy, you know that that's an impossible diagram. Okay, it doesn't represent a physical process, does not represent a physical process. Okay, this green is not a good color to write. Okay, is that clear? The same thing happens, okay, if you have...
Teacher,
yes?
can you repeat why is different from zero?
Oh, it's different. So, no, I made a mistake.
Zero.
I made a mistake.
It should be zero.
Right.
Okay.
Yeah. Okay, there is some confusion. For example, when just because of limitations of the drawing, but when you draw a tadpole, it looks like this. Okay, this is why I tend to write. Okay, when you draw a tadpole like this. So let me write here possible confusion. When you write a tadpole, you write it like this. Okay, and you put your arrow, I always put my arrow here to denote that this whole line is a whole line. Of course, when you draw the loop, then of course the arrow is going to go like this. It doesn't mean that a hole turns into a fermion, okay? This is just a limitation, okay? Limitation of the drawing. Limitation of drawing. But of course, a hole cannot turn into an electron without anything happening, right? Right. So this is why I always draw the arrow very close to here, and the same with the oyster. When you have the oyster, okay, just so you know the limitations of the drawing. I draw the oyster here, and I always draw the arrow here. So the position of the arrow is telling me exactly what kind of a particle is represented by that whole propagator, okay? And then you have, okay, let's put the slanted line here, okay? Just so that we don't get the lines messed up. Okay, so again, this is a hole propagator, and this is an electron propagator. The same with this. This is going to be, let me change, so do not draw like the line like this because it's confusing. You shouldn't put the arrow here, but the arrow where the sense of the type of particle you're going to have. So if you label this with an L, this L is less than Kf. Okay, is this clear? Here I pretend that this propagator is extending and doing something else with the diagram here. And I'll show you full diagrams to illustrate these cases more clearly. Okay, so is this clear? Again, this is a hole, so this is an intermediate momentum L, and this momentum is smaller than Kf. okay? While these here, if I label this with K, represent K greater than KL. Okay? Okay, so those, let's see if there's any other interesting case here. No, I think these are all the interesting cases. Okay? If you swap, for example, these arrows around, so if you put these two arrows on this side and these two arrows on this side, this will again be the oyster, so we can draw that one here, for example. So we have the interaction, okay? And we can put here and then, okay? And we can have the, for example, the K now coming in this direction, going out, and then going out here, coming in here with the L. This is also the oyster. And it's different from 0. Okay? Okay, so these are basically the kinds of things that can happen, and you can discard them by using the arguments we just made. Okay. Now look here. How can we look at the same problem from the second quantized point of view? Okay. So the second quantized view of this problem is, let's suppose you have this case here. Okay, let's suppose we have this. Okay, and we have the handles here. Okay, so this would be, we know that this cannot be possible. So if we inject K, we cannot have another particle above the Fermi C. We know that this would be above, this would be above the Fermi C. Okay, so let's represent what's going on here. So we inject in the particle in the single particle state in the system into the K state, and it comes into the interaction. So before the interaction happens, I need to have a particle in the state I'm injecting in. So this would be one, okay, particle in the state K. That would be the state, okay? And then I apply the interaction. So the interaction is going to be what? It's going to be, I remember this is R and R prime, okay? So we're going to have injecting the KL, so this would be KL in, okay? And extracting the KL in that same order. So we have this would be the matrix element, sort of looking the same matrix element that we have for the tadpole, okay? But then we have in the particle hole picture, particle hole, okay, formalism, then we would have, okay, so first we destroy a fermion, okay, above the Fermi C. So this would be the annihilation operator. And we also destroy another fermion in state K. This is one coming into the diagram like this. So these get destroyed. And then they create, in that order, in the order of that we build the operator, we need to switch, okay, the operators this way, because this is the form, okay, of a two-body, okay, second quantized operator. Okay, so now let's apply this, okay? So let's apply this. This was the way, remember this was KL, KL, but then the destruction operators were in the orders of these two labels here, but this one were switched. That was one rule that we had for the building of this second one quantized operator. This took care in particular of the correct sign of this of the resulting state. Okay, so let's apply this. We need to annihilate now a particle above the Fermi energy, but we have no other particle here. Okay, so if we apply this, so we need to annihilate something that doesn't exist. This gives 0. So this cannot happen. Okay, cannot happen. Is that clear? So this is the same conclusion that we arrived here. Why this? No, this one here. Why this this diagram was 0? So this is exactly the same with the K and the L, like this. So we cannot have a fermion coming out from nothing. If we inject a single fermion, another fermion cannot spontaneously appear above the Fermi energy. So that was the argument from the picture, and now this is the argument from second quantization. I introduce a particle, okay, propagator into the system. So we introduce a particle here in state K, and now it enters the interaction, okay? It enters the interaction, so this is the interaction, and now I apply the interaction to the initial state, and I would get 0. Okay, so that's how it works in second quantization. Let's see what happens now to this case. Okay, so this is a case that's going to be non-zero. We know. We inject this guy here, and now we have the other case like this. Okay, so let's try this this same diagram. So we have KL, KK, sorry, and L here. Okay, so this should be, again, this is greater than KF. This is smaller than KF. Okay, and so we would have now the single particle state. We inject again one particle in state K, and now we're going to apply the generic operators. So let me put it a little here above the expression. We'll put it in red. Okay, so we have the operator BKLMN, and then we have the second quantized form LK. You see, we switch again these labels here, M. Okay, so two-body operator. Okay, so now let's interpret the operator here. So let's write it also in generic form. The operator we want. So we have V KL, and this would be, for example, we can build the tadpole like this. Okay, KL, okay, and then we would have the C L K, okay, and then we would have the C K L, LK KL. This would be the order according to the form we have here. Okay, but now we have to interpret this in terms of the rules, right? So remember that the L is below, so let's emphasize here, L is below the Fermi energy, okay, and K is above the Fermi energy. Okay, so if we apply this operator, how do we translate? So let me rewrite again this one ket. Okay, so how do we translate in the particle Hall picture? Is we're going to destroy an electron below the Fermi energy. This would be exactly the same as creating a hole below the Fermi energy. Okay, So that would be the operator. Remember that there's a formula that connects the two. So the annihilation operator, okay, would turn into the creation of a creation of a hole below the Fermi energy. Remember the A's like here, these are fermions, okay, above, okay. K is above the Fermi energy. So A's will be operators creating electrons and destroying electrons above the Fermi energy, and B's will be creating and destroying holes below the Fermi energy, okay? So now this C here is turning into the creation of a hole. The destruction of an electron below the Fermi energy is the same thing as creating a hole below the Fermi energy. Then we need to destroy, okay, an electron above the Fermi energy. So this would be the A, K, okay? So that A is rather horrible here. So let's see, A, okay, okay? Now we translate this. Now we want to create an electron above the Fermi energy again. So this would be another A, K, now creation operator. And then we destroy a hole, we create a hole below the Fermi energy. So this would, we create an electron below the Fermi energy. So we're destroying a hole. Okay? So that will be the combination we need. Okay, and we write the matrix out. Okay, so now let's apply this. Is this clear how I obtained this operator here? Okay, so again, let's go over it quickly again. So this destroys an electron below. This is equivalent to creating a hole below, okay? Now this destroys an electron above. So this creates destroys an electron above, okay? Then we create an electron above. This is creating an electron above. And then this is destroying, this is creating an electron below. So if you create an electron below, it's because you're filling a hole. So you're destroying the hole, okay? So now let's apply this. So this first creates, so let me, don't have space here. So let me just do the first step. So let's apply these two operators here, okay? So, okay, let's do it on this side. We erase this equal sign. Okay, let me first tell you what's going to happen here, first step. So we apply these two operators. So this creates a hole below. Let me put it around here, okay? So we have one particle still, and this destroys the particles. I just write, so we create a hole below, so we have one hole, okay? And destroy the electron. So we're left with this, and then we write the rest of the operators, which would be creating another particle, okay, destroying a hole, and the amplitude. Okay? So this is the result of both of these. This creates a hole, so it creates a state, and then this destroys this occupation, so we're left with just one hole. Okay? Now we create an electron and then destroy this hole. So we're left with the KL, and then we're left with one K particle. And this is non-zero. Okay? So you see how we can interpret now this diagram here, or this piece of the diagram in terms of second quantization. We introduce the particle, okay? This is part of the, again, the propagator that's coming into this, into the interaction. And then we apply the interaction. We apply the interaction, which is here, and we just go along with the interaction and see what it does on the state. If it does this over the state, it just destroys, for example, here, we want to destroy some particle above the Fermi energy, which doesn't exist. This gives me 0. Here, there's no problem, okay? We first create a hole, okay, below the Fermi energy. So we create one hole here in the particle hole picture. Then we destroy the state, which we already have. Then we create the state again, and we destroy the hole we had. So we end up with the same state with some amplitude. Okay, this is actually what happens if you have just a single interaction in the system. You introduce the fermion above the Fermi energy. You have just a single interaction, and you exit. This would be the amplitude of that happening. Okay, is this clear? Any questions? So there will be like a few problems in the second problem set related to how to interpret these diagrams in terms of second quantized form. Okay. Okay. So let us now make some diagrams here and see whether. So we're going to see some examples. We're going to see that both the momentum balance, and when we see the momentum balance, we're going to analyze whether they're going to be zero or not. Some examples. Okay. So let's see. So let's see, for example, if we have this diagram here. In black now. Okay, and we have the interaction, the bubble. Okay, so we first start with the momentum balance. Okay, so we know that we have internal variables here, L and L prime. Okay, and we inject a momentum K. So here, for example, you can imagine, okay, momentum K, let's suppose some momentum goes up here, okay? So it goes up here. We create now an additional momentum L, and then this momentum L relinquishes whatever went in, and then it goes back down. So if we inject Q up, then it will be Q down again. So here we have Q equals to 0. There's no net momentum going into this diagram here, okay? So if no net momentum goes up here, then we need to have the same K on this side. And the same argument applies here. So if no momentum goes, no net momentum goes up and down there, okay? Then we have it going down here, okay? So you see, from the pictorial point of view, there's nothing that forbids this happening, okay? These are holes. We have just a single fermion going through the system with K greater than Kf. These are the L smaller, both of them are smaller than Kf, so there's no additional fermion above the Fermi C. We have zero momentum on these interactions, so the momentum is just going straight with these virtual processes going on there. So this is non-zero. Okay? Now let's see this guy. Let's see if we inject here. Okay? And now we have an interaction here. Okay? And now this is going back. Okay, we had this topic. One of the first problems we treated in the particle hole picture was something like this, and then there's another interaction here, and then this goes out like this. Okay. So let's label now this guy. So if we label this guy now, we have K going in, okay? Then we can apply the same argument. No momentum should go up here. So we have Q equals 0 in this interaction line. We have also Q equals 0 here. Okay, so what's a reflected momentum? If no momentum is taken away by this interaction, we have K here, okay? and then no momentum is taken away, so this is K again. Is this diagram possible? So here you apply the argument we said, okay, so imagine this is time, okay? And you draw a dotted line at a constant time, okay? So you would have something like this. And you see here that you have, at the same time, you have a hole and an electron with the same momentum. And this is not possible. You cannot have, because the hole is going to be below the Fermi energy, so it cannot have the same momentum as an electron above the Fermi energy, okay? Hole and electron with same energy or same momentum. Okay, which in this case is the same energy because these are free particle lines, okay? So this cannot happen, so this has to be zero. Okay? There's no way out, okay? This is more or less the same example. Let's see something more exciting like this. Let's suppose we have a line like this now going in, okay? And now we have something like this. And is this a possible diagram? Okay. So again, you inject, wait, I'm missing a line here. Okay. So I inject momentum K. So let's suppose some Q goes in here. Okay. Let's suppose some Q goes in here. Okay. So now we would have there's no momentum. We know here that there's no momentum because this is a dead end. So whatever goes in has to come out. So this is zero. So if this is zero, then what happens? The sum of these two has to be zero. So we would have some momentum going in, some momentum going out. So there's no momentum going this side. Whatever this is, P has to go in here and go out here. Okay? So if you have P going in and then P going out, then this also has to be zero, okay? Because at the end, this is a dead end also. It's a longer dead end, but it's a dead end, okay? So we have K coming out, okay? So is this possible? Now I'm going to ask you to participate. Do you know that I told you you have to sum up over all the possible diagrams you can imagine, but you have to have certain rules for that, okay? So you can't have diagrams that have this completely is this is impossible because of simply the energy spectrum you have, okay? So now, is this a possible diagram that we should have considered, for example? This is a second order diagram. So is it possible or not? Okay, I hope you still are there. At least tell me you are there.
Yes, I'm thinking.
Okay.
For these cases, P has the same energy, right?
Who?
The loop.
Which of the two are the loop with P, right?
Yes.
So that's right. So this is where where you can assess the impossibility of this diagram. We said this was a time t. At the same time, you have a hole with the same momentum as the electron. So this is also going to be zero. Okay, so this cannot happen. This cannot happen. And I've given you essentially the basic arguments that tell you that this cannot happen. What about this guy? This is another interesting situation. Draw it blue. I like blues. Okay, so if you have this, then you have your interaction line. Then you have, okay, then you have another interaction line. And then you have a propagator like this. Okay, so again, you have to analyze the momenta. So this is going to be a dead end. So this has to be a q equals 0. So k comes out again. But then you can have, for example, a p, for example, here. Let's suppose we have a p going in, okay? And then I have an arrow here, which is a L, okay? So if P, you take away L, you have P minus L here. And then you have P minus L go into here. We add L and we go it out as P. Okay? So this apparently could be a possible diagram, but there are two defects. Here, again, we have an electron which is above the Fermi energy. So we have now 2 electrons above the Fermi energy. This cannot be. So this is one reason. And the other reason is the same as the other diagrams. Okay? So we have, again, we draw this line here, and we have, but by a momentum conservation, we have both a particle and a hole with the same momentum. Okay, so this is doubly 0. Okay, this is 0 for 2 reasons. So you cannot have either this diagram either. Okay, let's see this one. Okay, so you know, I'm first going to draw one that we know that is non-zero. So let me just draw that one. We've done this with this one before. And let's see that. Let's make sure that one we know is different from 0. It's one of the polarization diagrams. Okay, why it is not 0. Okay, so now let's see if we have a consistent picture. We inject let me do it with another color. Let's do it with black this time. So we inject K, okay? Then I say that some Q momentum is going up here. So we end up with K minus Q, okay? K minus Q, and then I'm going to inject here, for example, momentum L, okay? So we inject here momentum L with Q. This will be Q plus L, okay? And then this goes down. It loses momentum Q, so now Q comes down here, combines with this K minus Q, and very nicely comes out to be K, okay? So you see that now we have 2 different momentum for the electron and hole. So one can be above the Fermi energy, one can be below the Fermi energy, okay? At each node, we have conservation of momentum. So everything works out. So this is different from 0. This is a polarization diagram. Okay, but now let's give it a twist, okay? And let's give it a twist in blue.
Teacher.
Yes.
Can you explain again with L, the part of L?
The part of L?
Where is, yes.
So remember that this is we're going to have an internal label, okay? So here, and so we have 2 internal labels here, which is Q and L, right? So I introduce this label, whatever momentum, a momentum that I have to integrate over. So I name it L, and then I inject it here. So I sum it, both of them, right? So Q is entering, L is entering, and out should come Q plus L, okay? Okay.
Yeah, okay. So L represents the arrow to the left.
Right, right. So let me make it a little larger so that it's not confusing.
Okay.
We have an arrow like this. Okay. Okay, so let's give this same diagram a twist. So let's suppose now we go with the momentum. Let's try to do it a little straighter. Okay, so we have momentum K. Then we're going to have an arrow like this. Okay, and then an arrow like this. Okay, and from here I'm going to have an interaction line coming. And from here, I'm going to have an interaction line coming. Okay, and here we're going to have something like this. Okay, and let's draw it this time like this. And we're going to put, so we come in with momentum K. We use the other color. Put it red now. So we come in with momentum K. Then if we take that, let's suppose now that we separate this like this. So there's various choices you can make, but I'm going to choose this one. So you can try another labeling. So if Q goes in this direction, so we inject with K, we take away Q, and now we're going to end up with K minus Q here, okay, in the interaction line, okay? Then we have to divide the momentum. So I again introduce the label L, so whatever, we're going to inject L here. So now we get K minus Q plus L, okay? And then, okay, we enter here, okay? And we subtract the L on this side, on this node, so we subtract the L. So K minus Q is coming down here. Okay, and it combines with Q and ends up having K. So is this 0 or non-zero? There's a problem with these classes, you know, the webinars is that I cannot see you thinking.
I think it's different from 0.
Yeah, there's no reason, right? Because here, for example, if we apply the argument of having a propagators at different electrons that hold with the same state, it's not true because one is Q and the other one's K, and they need not be the same, right? And here I have again Q and K, and here we have K and K. There's no contradictions arising here, okay? Momentum is conserved. This particle whole again have different momenta. So there's no reason for this one to be non-zero, so to be 0. So this is non-zero. This is another polarization diagram. Okay, when we will try to calculate. I'm going to let's see if we have time today, but we're going to try to write out this propagator, and you'll see that all these timings are going to be taken into account, okay? So you'll see that when we calculate the integral over here, we're going to take into account this diagram also, okay? And finally, the final example I'm going to do, let's see, is if one has something coming in, okay? And then we have an interaction line coming out here. And then from this interaction line, I have a propagator going out, okay? From this line, I have a propagator coming out of the first interaction. Then I have something like this, which I draw extra long so I don't get any interference, okay? And we have this is the diagram, okay? So again, let's do the momentum analysis here. So we have K going in, okay? And we assume that some Q goes out here, okay? And then we have K minus Q coming out here, okay? Here we know, let's call this L now. L is going to be 0 because this is a dead end, okay? So we need an additional arrow here to accommodate for the missing propagator I forgot. So the propagator goes back here like this, okay? And if this is 0, then we have k minus q. So anyone can jump in and say whether this is going to be 0 or non-zero. So this goes in like this, okay? And then this goes out. K minus q with the q goes out as a k. And here we can put an m for the loop, okay? So, and this one is going to be 0 because again, we have a particle and a hole with exactly the same momentum in this case, okay? Okay, so these are all the illustrations. Remember that when you want to decide whether a diagram is valid or not, you should label, see whether momentum can be conserved. For example, if I didn't put in this propagator, there's no way we could conserve momentum. So we were missing a propagator there. And then you just use the simple rules we've established, or use the second quantized form in order to determine whether that diagram is going to be 0 or not, okay? A systematic way of doing it. Okay, is this clear?
Yes, teacher.
Okay, good. Okay, so now the next exercise is to write, okay? Let's write the first, actually it's not the first, the second polarization diagram, because remember the oyster is the first, the second polarization diagram. Okay, because oyster is the first. Okay, so the second polarization diagram is going to be something like this. We've drawn it already. Let me draw it a little larger here so that we can. Okay, remember that we really don't need to calculate this full diagram because we did the pictures yesterday and we saw we only really need this piece here. So I'm just going to separate, okay, from analysis that we did yesterday, we only need this picture here. This is going to be, I'm going to write this in KT space, and this is going to be the last example I Fourier transform, but we really need this in K omega space, okay, for effective interaction. Okay, really only need, okay? So I'll show you the analysis we're going to do is to show you where this piece is going to come. Where is it going to come from? Okay? So let's write out. So we did this analysis just a couple of pages ago. So we have K coming in here. Now we have momentum Q here. So we have K minus Q. Okay? Then we label this as L. L goes into here. We have Q plus L. And then we subtract L and we end up with Q coming down. And the Q plus K minus Q is going to give me a K. Okay, so this is the full labeling in terms of the momenta. And additionally, we're going to put here a time. This is going to be time t and time t prime. This is going to be time t2. Okay, I'm just going to do this in KT space first, because there's I want to show you the condition for the conservation of omega, okay, which was too trivial before, okay? Here it's non-trivial. Okay, so let's write out this diagram. So this diagram, we have a fermion loop. So this is a closed fermion loop, so we have a -1, okay? Then we have two internal labels. We have L and Q. I chose another label here, so I'm going to get confused in the middle of the exercise if I mix L's with, okay, so we have, we're going to put here a P, we call it P, and P here, okay? Remember, those are all vectors, but I'm not going to clutter this diagram further, okay? So we have now a summation over the internal variables. We have a summation over P and Q, okay? And then we have an integration of over the intermediate times, okay? And then we start just drawing writing out the propagators, okay? So we have the first propagator, this one coming in, so I G0 plus, okay, K between T and T1, okay? First propagator, then we arrive at the first interaction. So the first interaction is going to be -I, just following the Feynman rules, okay? Then we can write the other propagator, which is going to be this one here. So I, G, G0 plus, then K minus Q, okay? And then this is going to be between T prime and T. Okay, and then so we reach. Let's write out now the other two propagators here. Okay, so this is multiplied I G0 plus, and then we get P, for example, is going to be the first. Okay, and then P is going to be T prime minus T. And then we have the other propagator, which is 0, 0 plus, and this is going to be P plus Q. And this is going to be T prime minus T. Okay, so we have 1, 2, 3, 4. 1, 2, 3, 4 propagators. We're just missing one. Okay, so we put in the second interaction line, I, B of Q again, okay, times the propagator, the remaining propagator, which is an I here, G0 plus, and then K, T2 minus T prime. Okay, so this is the full expression. Okay, so we now define the Fourier transform. So the Fourier transform in KT space is going to be defined by 1 over 2 pi d omega I omega t, then G0 plus okay of K and omega. Okay, so everything here is a function of K and T. Everything is a function of K and T. So now we substitute whatever K we have here, we introduce here, and whatever T we have, or combinations of T, we put in the exponent here. So we substitute this into this expression here. And I'm not going to do all that substitution because that's lots of algebra there that you know how to do that. But I'm going to write an intermediate step so you can follow. Okay, so we're going to have this. Okay, so we write again the sum over Q's and P's. Okay, and then we have how many frequency integrals here? Notice that we're going to have each time I introduce a Green's function, I'm going to have a omega here, omega prime, okay, omega double prime, omega triple prime, and omega 4 prime. Okay, each one introduces a different frequency, So I'm going to have 4 frequency integrals. Okay, omega, omega prime, omega double prime, omega triple, triple prime. We have 5 propagators, so we have 5 frequency integrals. Okay, then we can take out from here, and notice I'm pushing to the right the time integrations. So I have G0 plus, and then we have the first momenta, the first labels here. Then we have the second labels. None of this involves time, so we can take them out from the time integrals. So k minus q omega prime. Okay, and then we're going to have I G naught plus. I'm going to have P plus Q. Okay, and we're going to have omega double prime. Okay, and then almost finished here, so 0 plus, then we have the momentum P, triple prime. Okay, then I'm just going to write the interaction here, which is the same interaction because it's associated with the same Q squared. Okay, and then we have the last propagator here, which will be I G naught plus K and omega 4. Okay, then I'm going to write the exponentials that do not involve the time, the integrated times, which are the intermediate times. So we'll have e to the I omega 4, okay, times t2 exponential of minus I omega t1, okay? And then we have the integrations that we need. So dt, these are the only ones that don't involve t. The other ones, all the intermediate ones involve t, either t or t prime. So we get I, t, okay? And then we get this combination omega minus omega prime minus omega double prime minus omega triple prime, okay? And then we get the last integral, which is dt prime, and we get I t prime, and we get omega prime plus omega double prime, okay, minus omega triple prime minus omega 4. Okay, so this is the full expression, and we know how to solve this. This is here delta, and then I'm going to write it like this. So this is delta omega. Made a mistake here. This is a plus here. Okay, omega plus omega triple prime. Okay, comma omega prime plus omega double prime. Okay, and here the same. Okay, so we have delta Okay, so in the Fourier transform, I put this 2 pi here, so that 2 pi is going to cancel with 2 pi's that are going to come up here. Okay. You sort out, okay, the 2 pi's that are going to come from the deltas. Okay, so this is going to be now delta omega prime, and then omega triple prime plus omega 4. Okay, this is not so clear. omega 4. Okay, so we have that now these two conditions. I have 5 integrations here. We have 2 conditions here. Okay, let's see, 2 conditions. Okay, and we have 2 summations of the internal moment. Okay, so let's sort out this conservation here. Okay, that we have here. So let me just put the diagram again, and I'm going to label how the momenta correspond to the frequencies that we have here, so that we have no confusion. So let me write it here with so we have the propagator, we have the interaction line, okay? So here we have the diagram. So we know that the first one we have K omega. So this incoming line is going to be K omega. Let me write it with the color here so it is clear. So we have K omega coming in here. Then the K minus Q, which is this line here, is going to be accompanied by omega prime. So this is K minus Q and omega prime, okay? And then, for example, the one coming out will be K. This will be K and omega 4, okay? K and omega 4 here, okay? And then we have this intermediate momentum. So this momentum is going to be P, okay? And it's going to be associated with a P with a triple prime. I should have drawn this diagram a little larger. This, my pen is not fine enough. So here we have triple prime, okay? And then we have P plus Q here, okay? And P plus Q, where is P plus Q here? It's associated with omega double prime. So very good, we have here, and now we have the momentum here, Q, okay? And the momentum here, Q, okay? Coming down. Okay, and we will see that we were going to have to associate some momentum to some frequency to this. I'm not going to put that in yet. Okay. So let's see that the two frequency conditions. Okay, so the first one is going to be a omega prime, okay, plus omega double prime is equal to omega triple prime plus omega 4. Okay, this is this condition here. Okay, and the other condition is this one here. So we have omega prime, and we're going to write it like this: omega prime minus omega. This one. Omega prime, let me see 1 second. So omega prime plus triple prime, right? So this is going to be, the other condition is going to be omega prime minus omega. It's going to be omega triple prime minus omega double prime. So you see from this condition here, you get this. So I just move this omega prime to this side and the omega triple prime to the other side, okay? I moved this one, omega, to this side, so omega prime minus omega, and we move the double prime to this side, so we'll have omega triple prime minus omega double prime. Okay, is this clear? So,
Yes.
okay, so I'm going to name this difference here, and I'm just going to see that the labeling I'm going to choose is going to be consistent. Okay, so I'm going to name this omega prime minus omega. I'm going to call it minus epsilon. Okay, and I'm going to leave this side like this. Okay, okay, chose. Okay, now I'm going to just switch these two, and so epsilon, if I multiply by -1 on both sides, we get omega double prime minus omega triple prime. Okay, now I'm going to call triple prime, I'm going to call beta. Okay, and I put the minus sign, so I call this beta, and I'm going to call this beta plus epsilon. Okay, so you see that now here this double prime here is going to be, double prime is going to be beta plus epsilon. Okay, and this triple prime here, we use another color here. So this triple prime here, I'm going to call epsilon. Okay, sorry, I'm going to call beta. Okay, this is what I call them here. So you see that if I make that choice, then beta plus epsilon minus beta gives me epsilon. So everything, this relationship is satisfied. Okay? So what I have to now show is that the other relationship is satisfied. So let's make here an aside. Okay? Okay, so let's substitute the same values up here. So omega prime is going to be omega minus epsilon. Okay, so now we see this relationship here. Okay, so omega prime, I chose this difference to be omega prime minus omega is minus epsilon. So omega prime is omega minus epsilon. So we have here omega minus epsilon, okay? Then we have plus omega double prime. Omega double prime was equal to beta plus epsilon, okay? And this is going to be equal to, on the other side we have omega triple prime. Omega triple prime is beta, okay? And omega 4 is going to be, you see here, all these processes happen here. We enter with k omega, and if the energy is going to be conserved, omega 4 has to be equal to omega. So we get omega here, okay? It is going to be equal to omega 4, okay? So you see, let's see what happens. So this cancels with this, and we get omega plus beta is beta plus omega. Okay, so good. So this choice of parameters here satisfies both restrictions. Okay, is this clear what I did? So I started with this restriction. I relabeled my omega as epsilons here. Okay, and we satisfy with this choice of epsilon beta, which are the internal variables here to integrate over. Okay, we're going to have now just these two variables, epsilon and beta, and both of these restrictions are satisfied with this choice. Okay, so we now finish labeling this. So you see here that if this is omega minus omega prime, so if omega minus omega prime, what is this? Omega minus omega prime is epsilon, right? So if you come in with omega, you take away omega prime, so this has to be epsilon. Okay? This goes into here. Omega 3 is beta, so here we add with epsilon, so beta plus epsilon is precisely this, okay? Beta coming in here, epsilon coming up here, so we get beta plus epsilon. Then we take away beta, so we come down here again with epsilon, okay? And then we add here omega prime is going to be omega minus epsilon, okay? So we have, this is going to be omega minus epsilon, okay? And we add epsilon coming down, so we get omega here. Perfect. Okay? So this is how we settle both momentum conservation and energy and omega conservation or frequency conservation, which is going to be the eigenvalue of the fully interacting problem. Okay? Is this clear? Do you have any questions? So before I write this final answer here, we are left with the following expression. Okay? So there's two frequency integrations. See, I'm missing one. Oh, no. Okay, so see, the other one is omega. Okay? So you have both propagators here, the incoming one and the outcoming one that have the same combination k omega. This is squared, okay? Then we have the summation over P and Q. Q and P, okay? And then we have one integral over epsilon, okay? We're going to be left with a couple of factors of 2 pi, and the other one's going to be integral over beta, okay? And then we have the propagators that involve those variables to be integrated over. Okay, so I'm going to write this final expression, and I'm going to relieve you from further manipulations here so that you can digest this. And then next class, we're going to see what, what's going on? Okay. What integrals we have to do. So as we, are lazy, we want to identify the minimal amount of work we need to do. So we're going to identify it from this integral here. Okay, and we have okay, so let me just write this this result here so that we're sure that we have all the correct labeling. So now let me not commit the same mistake. I'm going to write a big ass diagram here. It's really clear. Okay, so this is the diagram in k omega space. Okay, so we have k omega coming in here, k omega coming out here. We have a q and epsilon going in here. So we have k minus q and omega minus epsilon going out here. Then we inject beta into here. So and we have the internal labels P beta, okay? And now we add with Q and epsilon, so we get P plus Q, and then we get epsilon plus beta, okay, above here. And then we subtract P and beta, and we, so I forgot to put the arrow here. So now we have a down-going arrow with Q and epsilon again. Okay, we inject it into here, and we add these two variables here, so we end up with P and Q. So this will be the expression, okay? We obtain from KT space without using the Feynman rules in KT space. We did the Fourier transform, and we obtained the Feynman rules in reciprocal space. Okay, so we have this situation, and this will be the integral we have to do in order to calculate this diagram. Again, this diagram is going to be made up of pieces, okay? Pieces that are joined by the integrals over P, beta, the sums over P and Q, and the integrals over epsilon and beta, okay? So we will just need this piece in order to calculate the dielectric constant. We will just need this little piece from here. So it's the P beta piece, which is going to be an integral, and the P plus Q beta plus epsilon. Okay, and the Q epsilon here. Okay, this is what we're going to need, and this is going to be the I pi 0 integral. Okay, so this we will do next time. Next time we do this, and we'll identify this piece here, and then from this piece we will be able to calculate the dielectric constant. With the minimal work possible, dielectric constant. Although doing the full integral will be interesting, because this is an exercise in complex integration, okay? So we need to review a little bit of complex integration, even to do this diagram also. So I think you will appreciate seeing what all what you learned in complex analysis is applied to some physics, okay? Okay, so any questions? Comments? Didn't understand any piece of the expansion we did of the diagram? Momentum conservation. Nope.
One thing, teacher, I think that you made a mistake in one of the first boards at the beginning when we were saying that it was different or zero. Yes, in this case, in the first case.
Yeah, it's true.
It's equal, right?
I kept making the same mistakes. Let me correct this. So that the class is finally in the good shape. Equals to 0. What else? So this is also 0. Okay, this one is different from 0. That's a tadpole, and that is the oyster. So this is different from 0, and this is 0. Okay, that's I think the only mistakes that were left. Any other mistakes?
Yes, no, the only one.
What? Here?
No, it was the only one.
It was the only one. Okay, good. Okay. Any other comments, questions? Okay, so you see you need some ability with the labeling here, because we have so many frequencies here. We have to reduce them to just a couple of frequencies and combinations of those frequencies using these conditions. Remember that this omega integration here is the external integration, so we have the Fourier transform. So this is why we this omega, when we go from KT space to K omega space, we eliminate this first integration here, and we're left with 4 integrals here: omega prime, double, triple, and fourth, quadruple frequencies. But then we have 2 conditions, so we're left with 2 frequencies. That's what's going on here. Okay, so that's why we only have 2 frequencies here instead of 3. Okay. Okay. So if you have no other questions, please sit down and do this carefully, because very important results are going to come out from here. So we're going to see how these polarization diagrams yield the correct screening effect, and thus the correct dielectric constant of the interacting electron system, okay? Okay, so have a good Holy Week, okay? Please take care and see you on Tuesday.
Bye, teacher.
Okay.
Yes, teacher, thank you.
Bye-bye.
Solamente quisiera para
Bye, teacher.
Bye-bye.